Hello YouTube, my name is Neil and we're studying for the MCATs today. We're in the Organic Chemistry Review, Chapter 12, Separations and Purifications. We spent a lot of time discussing how to theoretically get various products from a range of reagents. However, as we're sure you've learned in your organic chemistry labs, chemistry isn't as straightforward in the real world as it is on paper. Much of the time spent in the lab is dedicated to the isolation and purification of the desired product after the reaction has occurred. Throughout this chapter, we will discuss several techniques for this. Good news, though, this isn't a lab practical on the MCAT, of course. All you need to understand is when these techniques are used and how they work. Solubility-based methods. Solubility-based methods versus, let's see what the other chapters are real quick. Distillation, chromatography. Solubility-based methods. One of the simplest ways to separate out a desired product is through extraction. The transfer of a dissolved compound, the desired product, from a starting solvent into a solvent in which the product is more soluble. Extraction is based on the fundamental concept that like dissolves like. This principle tells us that a polar substance will dissolve best in polar solvents, and a nonpolar substance will dissolve best in nonpolar solvents. These characteristics can be taken advantage of in order to extract only desired product, leaving most of the impurities behind in the first solvent. Extraction. Which is defined as transfer of a dissolved compound from a starting solvent into a solvent in which it is more soluble. Transfer of just transfer to more soluble solvent. When we perform extractions, it is important to make sure the two solvents are immiscible, meaning they form two layers that do not mix, like water and oil. The two layers are temporarily mixed by shaking so that solute can pass from one solvent to the other. For example, in a solution of isobutyric acid and diethyl ether, shown in figure 12.1, we could extract the isobutyric acid and with water. Isobutyric acid with its polar carboxyl group is more soluble in a polar solvent like water than in a nonpolar solvent like ether. When the two solvents are mixed together, isobutyric acid will transfer to the water layer, which is called the aqueous layer. The nonpolar ether layer is called the organic phase or layer. Solvents are immiscible, meaning they don't mix. The aqueous layer polar. Organic layer is nonpolar. Like dissolves like. Isobutyric acid and diethyl ether, which has an oxygen. Isobutyric acid has the hydrogen to make hydrogen bonds, so that is more miscible in water. So it'll like to go into that phase. After the two layers are mixed together, how do we then get the desired product out? The water, aqueous, and ether organic phases will separate on their own, given time to do so. In order to isolate these two phases, we use a piece of equipment called a separatory funnel, as shown in figure 12.2. Gravitational forces cause the dense layer to sink to the bottom of the funnel, where it can then be removed by turning the stopcock at the bottom. It is more common for the organic layer to be on top, although the opposite can also occur. Remember that the position of the layers is determined by their relative densities. In this example, we'll assume that the aqueous layer is more dense and settles to the bottom of the separatory funnel. Once we drain the aqueous layer from the separatory funnel, we repeat the extraction several times. Additional water is added to the separatory funnel. It is shaken and allowed to settle, and the aqueous layer is once again drained off. This is done in order to extract as much of the isobutyric acid from the ether layer as possible because it does not completely transfer with the first extraction. Multiple extractions with fresh water are more effective for obtaining the most product rather than a single extraction with a large volume of water. You can imagine this as analogous to laundering dirty clothes several times rather than laundering them with more water. The cleaner each volume of water is, the less dirt is likely to be left on the clothes afterwards. Once the desired product has been isolated in the solvent, we can obtain the product alone by evaporating the solvent, usually by using a rotary evaporator, rotovap. Let's write down some of these things. Separatory funnel, rotary evaporator. Another way to take advantage of solubility properties is to perform the reverse of the extraction we just described in order to remove unwanted impurities. In this case, a small amount of solute is used to extract and remove impurities rather than the compound of interest. This is called a wash. So if the desired product was not in the bottom aqueous layer, and we were cleaning what was in the organic layer by taking out impurities into the aqueous layer. Other methods, in addition to extraction, filtration, and recrystallization, make use of solubility characteristics to separate compounds from a mixture. Filtration isolates a solid from a liquid. In the chemistry lab, one pours a liquid-solid mixture onto a paper filter that allows only the solvent to pass through, much like a coffee filter. At the end of filtration, one is left with the solid called the residue and the flask full of liquid that passed through the filter, known as the filtrate. Filtration can be modified depending on whether the substance of interest is the solid or is dissolved in the filtrate. Gravity filtration, in which the solvent's own weight pulls it through the filter, is more commonly used when the product of interest is in the filtrate. Hot solvent is generally used to keep the product dissolved in liquid. Vacuum filtration, in which the solvent is forced through the filter by a vacuum connected to the flask, is more often used when the solid is the desired product. Recrystallization. Recrystallization is a method for further purifying crystals in solution. In this process, we dissolve our product in a minimum amount of hot solvent and let it recrystallize as it cools. The solvent chosen for this process should be one in which the product is soluble only at high temperatures. Thus, when the solution cools, only the desired product will recrystallize out of solution, excluding the impurities. Extraction, filtration. What must be true about the two solvents used for an extraction to work? For an extraction to work, they must be immiscible. When doing an extraction, would it be better to do 3 extractions with 10 milliliters of solvent or 1 extraction with 30 milliliters? I guess 3 extractions with 10 milliliters. 3. Would acid dissolve better in aqueous acid or aqueous base? Why? Would acid dissolve better in aqueous acid or aqueous base? Acid and base would neutralize, but in acid less of the hydrogens would deprotonate. In a base, more hydrogens would deprotonate. And that's what we're calling dissolve in the case, right? So I guess in an aqueous base, I'm going to go with aqueous base. Let's check the answers to those. Two solvents must be immiscible. It's better to have 3 washes of 10 milliliters. Acid dissolves better in aqueous base because it will dissociate to form the conjugate base, and being more highly charged will become more soluble. Note that like dissolves like applies to polarity. Acids and bases dissolve more easily in solutions with the opposite acid-base characteristics. Right. All right. 12.2, distillation. Extraction requires 2 solvents that are immiscible in order to separate the product. But what happens when the product itself is a liquid that is soluble in the solvent? This is where distillation comes in handy. Distillation takes advantage of differences in boiling point to separate 2 liquids by evaporation and condensation. The liquid with the lower boiling point will vaporize first, and the vapors will rise up the distillation column to condense in a water-cooled condenser. This condensate will then drips down into a vessel. The end product is called the distillate. The heating temperature is kept low so that the liquid with the higher boiling point will not be able to boil and therefore will remain liquid in the initial container. This is the process that is used to make liquor at a distillery. Because ethanol boils at a lower temperature than water, we can use distillation to make beverages with high ethanol contents. Condensate and distillate. Whoops. Distillate. So is the condensate also the distillate? I guess it could be. It just depends. The distillate just depends on what you want. The condensate is the one that evaporizes first. If that happens to be your product that you want, then I guess it's also the distillate. But it doesn't have to be. If you wanted the original, or the one with the higher boiling point, that could be considered the distillate. The heating temperature is kept low. We already went through that. Simple distillation. Simple distillation, as the name indicates, is the least complex version of distillation. It proceeds precisely as described above. This technique should only be used to separate liquids that boil below 150 degrees Celsius and have at least 25 degrees difference in boiling point. These restrictions prevent the temperature from becoming so high that the compounds degrade and provide a large enough difference in boiling points that the second compound won't accidentally boil off into the distillate. The apparatus for this technique consists of a distilling flask containing the combined liquid solution, a distillation column consisting of a thermometer and a condenser and a receiving flask to collect the distillate. The setup is the same as shown in figure 12.3, sans the vacuum adapter. Sometimes an additional piece of equipment such as a boiling chip, ebuliator, or magnetic stirrer will be introduced to break surface tension and prevent superheating. Superheating occurs when a liquid is heated to a temperature above its boiling point without vaporization. Superheating situations occur when gas bubbles within a liquid are unable to overcome the combination of atmospheric pressure and surface tension. So superheating is also a case in which you would damage your products. So you avoid it. Let's write down some of these tools. Distilling flask, distillation column, condenser, receiving flask, and superheating. We have vacuum distillation, where water, so the vacuum would be over here on the right side, right before the receiving flask. Fractional distillation, we'll get to that next. Where's the simple? We don't have a picture of the simple. I guess the simple just wouldn't have the vacuum. We use vacuum distillation whenever we want to distill a liquid with a boiling point over 150 degrees Celsius. By using a vacuum, we lower the ambient pressure, thereby decreasing the temperature that the liquid must reach in order to have sufficient vapor pressure to boil. This allows us to distill compounds with higher boiling points at lower temperatures so that we do not have to worry about degrading the product. The apparatus for vacuum distillation is shown above in figure 12.3. Fractional distillation. To separate two liquids with similar boiling points less than 25 degrees apart, we use fractional distillation. In this technique, a fractionation column connects the distillation flask to the condenser, as shown in figure 12.4. A fractional column is a column in which the surface area is increased by the inclusion of inert objects like glass beads or steel wool. As the vapor rises up the column, it condenses on these surfaces and refluxes back down until rising heat causes it to evaporate again, only to condense again higher in the column. Each time the condensate evaporates, the vapor consists of a higher proportion of the compound with the lower boiling point. By the time the top of the column is reached, only the desired product drips down to the receiving flask. So here, the product, your desired product, is going to drip down into the back down into the container, and what we're boiling off is just wasted. I mean, I guess you're still going to have the rest of the apparatus and a receiving flask. It looks like here the desired product is in this flask. So maybe you don't even need a receiving flask. I mean, you still need to waste it somehow. You're still going to have something on the end. You might not have to have an ice bath. But I guess you could just add this part to this and get a more efficient distillation of this part if you really care about this part. With increased surface area in the distillation column, distillate has more places to condense on its way up the column. This allows for more refined separation of liquids with fairly close boiling points. All right. We use vacuum distillation for greater than 150 degrees Celsius. We use fractional distillation when the difference in boiling points is less than 25 degrees Celsius. Boiling point, let's write difference in boiling point. Distillation separates compounds based on what property? Their boiling points, differences in boiling points. If we are given a solution of ether with a boiling point of 308 Kelvin and a methylene chloride with a boiling point of 313 Kelvin, which type of distillation should be used to separate them? Well, 13 minus 8 is like 5, so that's less than 25 degrees, so we should use fractional distillation. Number 3, if we are given a solution of bromobenzene with a boiling point of 156 degrees Celsius and camphor with a boiling point of 204 degrees Celsius, which type of distillation should be used to separate them? 4 plus 200 minus 56 is like 44, so 48 degrees, so there's enough difference. But the boiling point of bromobenzene is 156. So, and camphor is 204, so they're both above 150, so vacuum distillation will be used in this case. 12.3, chromatography. Chromatography is another tool that uses physical and chemical properties to separate and identify compounds from a complete mixture. In all forms of chromatography discussed here, the concept is identical. The more similar a compound is to its surroundings, whether by polarity, charge, or other characteristics, the more it will stick to and move slowly through its surroundings. The process begins by placing the sample onto a solid medium called the stationary phase or adsorbent. We then run the mobile phase, usually a liquid or a gas in gas chromatography, through the stationary phase. This will displace or elute the sample and carry it through the stationary phase. Depending on the characteristics of the substance in the sample and the polarity of the mobile phase, it will adhere to the stationary phase with differing strengths, causing the different substances to migrate at different speeds. This is called partitioning, and it represents an equilibrium between the two phases. The different compounds will have different partitioning coefficients and will elute at different rates. This results in separation within the stationary phase, allowing us to isolate each substance individually. Let's write some of these down. Chromatography. We got the stationary phase. The absorbent. We have the mobile phase. We have the word elute, which means displace. Partitioning. And a partitioning coefficient. There are many different media that can be used as the stationary phase, each one exploiting different properties that allow us to separate out the desired compound. On the MCAT, the property most commonly used is polarity. For instance, thin layer chromatography, TLC, which we will shortly discuss, uses silica gel, a highly polar substance, as its stationary phase. Cellulose, another polar substance, may also be used. This means that any polar compound will adhere to the gel well and thus move through elute slowly. When using column chromatography, size and charge both have a role in how quickly a compound moves through the stationary phase. Chromatography can use even strong interactions, such as antibody-ligand binding. Let's write down a few of these examples. Thin layer chromatography uses silica gel. Cellulose. And the property here is polarity, because these are both polar. And we also can use size and charge in column chromatography. Which uses charge and size. Antibody-ligand is another example. As mentioned earlier, chromatography is based on the speed at which compounds move through media. In practice, however, we will measure either how far each substance travels in a given amount of time, such as in TLC, or how long it takes to elute, as in column or gas chromatography. Should we write that down? That thin layer is literally using the distance traveled versus gas liquid chromatography, as in column or gas chromatography. You're using time. The types of chromatography that we will discuss include thin layer and paper chromatography, column chromatography, gas chromatography, also called gas liquid chromatography, and high performance liquid chromatography, or HPLC. Thin layer and paper chromatography. Thin layer chromatography and paper chromatography are extremely similar techniques, varying only in the medium used for the stationary phase. For thin layer chromatography, a thin layer of silica gel or alumina adherent to an inert carrier sheet is used. For paper chromatography, as the name suggests, the medium used is paper, which is composed of cellulose. For these techniques, the sample that we want to separate is placed directly on the adsorbent itself. This is called spotting because we apply a small, well-defined spot of the sample directly onto the silica or paper plate. The plate is then developed, which involves placing the adsorbent upright in a developing chamber, usually a beaker with a lid or a wide-mouthed jar. At the bottom of the jar is a shallow pool of solvent called the eluent. Let's write that down. Eluent. The spots of sample must be above the level of the solvent, or else they will dissolve into the pool of solvent rather than running up the plate. When set up correctly, the solvent will creep up the plate by capillary action, carrying the various compounds in the sample with it at varying rates. When the solvent front nears the top of the plate is removed from the chamber and allowed to dry. As mentioned before, TLC is often done with silica gel, which is polar and hydrophilic. Let's write that down as well. Polar, hydrophilic. Whatever, good enough. I'm going to write this again. The mobile phase, on the other hand, is usually an organic solvent of weak to moderate polarity, so it doesn't bind well to the gel. Because of this, nonpolar compounds dissolve in the organic solvent and move quickly as the solvent moves up the plate, whereas the more polar molecules stick to the gel. Thus, the more nonpolar the sample is, the further up the plate it will move, as shown in figure 12.5. Mobile phase would be the eluent. And in this case, it is organic and nonpolar. Reverse phase chromatography is the exact opposite. In this technique, the stationary phase used is nonpolar, so polar molecules move up the plate quickly, while nonpolar molecules stick more tightly to the stationary phase. The spots of individual compounds are usually white, which makes them difficult or impossible to see on the white paper or TLC plate. To get around this problem, the developed plate can be placed under ultraviolet light, which will show any compounds that are ultraviolet sensitive. Alternatively, iodine, phosphomolybdic acid, or vanillin can be used to stain the spots, although this will destroy the compounds such that they cannot be recovered. Reverse phase chromatography is when stationary phase, the adsorbent, nonpolar. Eluent is polar. When TLC is performed, compounds are generally identified using the retardation factor, RF, which is relatively constant for a particular compound in a given solvent. The RF is calculated using the equation RF equals distance spot moved divided by distance solvent front moved. So the ratio of the spot to the solvent's distance. Let's write that down. RF, retardation factor, equals distance spot, distance to spot, over distance to front. I'm going to say distance to eluent. Because its value is relatively constant, the RF value can be used to identify unknown compounds. This technique is most frequently performed on a small scale to identify unknown compounds. It can also be used on a larger scale as a means of purification, a technique called preparative TLC. As the large plate develops, the larger spot of sample splits into bands of individual compounds, which can then be scraped off and washed to yield pure compounds. Thin layer and paper. And here we have column chromatography. The principles behind column chromatography are the same as for thin layer chromatography, although there are some differences. First, column chromatography uses an entire column filled with silica or aluminum beads as an adsorbent, allowing for much greater separation. The setup for this is shown in figure 12.6. In addition, thin layer chromatography uses capillary action to move the solvent up the plate, whereas column chromatography uses gravity to move the solvents and compounds down the column. To speed up the process, one can force the solvent through the column using gas pressure, a technique called flash column chromatography. In column chromatography, the solvent polarity can also be changed to help elute the desired compound. So here we have solvent on top of sand, alumina or silica, and sand at the bottom, with some glass, wool, or cotton, a stopcock to control flow, and a collection flask. Samples added at the top of the column, and a solvent is poured over it. The more similar the sample is to the mobile phase, the faster it elutes. The more similar it is to the stationary phase, the more slowly it will elute, if at all. Eventually, the solvent drips out of the end of the column, and the different fractions that leave the column can be collected over time. Each fraction will contain different compounds. After collection, the solvent can be evaporated, leaving behind the compounds of interest. Column chromatography is particularly useful in biochemistry because it can be used to separate and collect macromolecules such as proteins or nucleic acids. There are several techniques that can be used to isolate specific materials, which are described in the following paragraphs, as well as in Chapter 3 of Biochemistry. Ion exchange Chromatography. In ion exchange chromatography, the beads in the column are coated with charged substances so that they attract or bind compounds that have an opposite charge. For instance, a positively charged compound will attract and hold a negatively charged backbone of DNA or protein as it passes through the column, either increasing its retention time or retaining it completely. After all other compounds have moved through the column, a salt gradient is used to elute the charged molecules that have stuck to the column. I'm just going to write negatively charged DNA/protein. Uses a positively charged compound. Size exclusion chromatography. In size exclusion chromatography, the beads used in the column contain tiny pores of varying sizes. These tiny pores allow small molecules to enter the beads, thus slowing them down. Large compounds can't fit into these pores, so they will move around them and travel through the column faster. It is important to remember that in this type of chromatography, the small compounds are slowed down and retained longer, which may be counterintuitive. The size of the pores may be varied so that molecules with different molecular weights can be fractionated. A common approach in protein purification is to use an ion exchange column followed by a size exclusion column. In size exclusion, chromatography, we use pores, smaller molecules move slower. Affinity Chromatography. In affinity chromatography, a protein of interest is bound by creating a column with high affinity for that protein. This can be accomplished by coating beads with a receptor that binds the protein or a specific antibody to the protein. In either case, the protein is retained in the column. Common stationary phase molecules include nickel, which is used in separation of genetically engineered proteins with histidine tags, antibodies or antigens, and enzyme substrate analogs, which mimic the natural substrate for an enzyme of interest. Once the protein is retained in the column, it can be eluted by washing the column with a free receptor or a target or antibody, which will compete with the bead-bound receptor and ultimately free the protein from the column. Eluents can also be created with a varying pH or salinity levels that disrupt the bonds between the ligand and the protein of interest. The only drawback of the elution step is that the recovered substance can be bound to the eluent. If, for example, the eluent was an inhibitor of an enzyme, it could be difficult to remove. Nickel is used for histidine. And the eluent can be also an antibody or target, as well as pH and salinity. Gas chromatography. Gas chromatography, or GC, is another method that can be used for qualitative separation. GC, also known as vapor phase chromatography, VPC, is similar to the other types of chromatography and is shown in figure 12.7. The main conceptual difference is that the eluent is a gas, usually helium or nitrogen instead of a liquid. The adsorbent is a crushed metal or polymer inside a 30-foot column. This column is coiled and kept inside an oven to control its temperature. The mixture is then injected into the column and vaporized. The gaseous compounds travel through the column at different rates because they adhere to the adsorbent in the column to different degrees, and will separate in space by the time they reach the end of the column. The injected compounds must be volatile, low melting point, sublimable solids, or vaporizable liquids. The compounds are registered by a detector, which records them as a peak on a chart. Let's write down a quick summary of that. So let's say gaseous sample and eluent move through solid or liquid adsorbent. It is common to separate molecules using GC and then to inject the pure molecules into a mass spectrometer for molecular weight determination. Mass spectrometry involves the ionization and fragmentation of compounds. These fragments are then run through a magnetic field which separates them by mass to charge ratio. The total molecular weight can thus be determined, or the relative concentrations of the different fragments can be calculated and compared using reference values to identify the compound. Mass spectrometry to identify compounds. High performance liquid chromatography, Hplc. Hplc was previously called high pressure liquid chromatography. As the name suggests, high performance versus high pressure. As the name suggests, the eluent is a liquid and it travels through a column of a defined composition. There are a variety of stationary phases that can be chosen depending on the target molecule and the quantity of material that needs to be purified. This is fairly similar to column chromatography because the various compounds in solution will react differently with the adsorbent material. In the past, very high pressures were used, but recent advances allow for much lower pressures, hence the change in name. In HPLC, a small sample is injected into the column and separation occurs as it flows through. The compounds pass through a detector and are collected as the solvent flows out of the end of the apparatus. The interface is similar to that used for GC. Because the entire process is computerized, we use a liquid under pressure instead of gas. Because the whole process is under computer control, sophisticated solvent gradients as well as temperature can be applied to the column to help resolve the various compounds in the sample. Hence the higher performance of HPLC over regular column chromatography. So it's similar to column chromatography. Looks like a liquid eluent. Down, solid, column, adsorbent. I'm sure you can coat it with stuff just like in the column chromatography case. Before you move on, number 1, what properties of molecules do thin layer chromatography, paper chromatography, and standard column chromatography take advantage of to separate compounds? They're different adherence to the adsorbent based on polarity in the case of thin layer chromatography and paper chromatography, and charge and size in the case of column chromatography. What are the 3 specialized types of column chromatography? What does each use in order to separate the sample? In column chromatography, ion exchange chromatography uses positively charged adsorbent to attract negatively charged DNA, so you're using charge. In size exclusion, you're using pores to separate smaller molecules from bigger molecules, so that's just size. Affinity uses affinity to specific receptors, antibodies and antigens, or proteins and receptors. Are these the only 2 cases? Enzyme and substrates. Enzymes and substrates. All right. In what way is gas chromatography distinct from all of the other techniques we have discussed? Gas chromatography is different in that your products are not really recoverable at the end. You're vaporizing them and using a computer or using a detector and a computer to quantify them. But I don't think you have a recoverable product at the end. We'll check the answers on that. What is the major historical distinction between HPLC and column chromatography, and what is the major distinction now? HPLC uses liquid. It used to use high pressure liquid, but now with new techniques, it's just called high performance. Historical distinction and current distinction. Even though it doesn't use high pressure, it's still using liquid. That would be the distinction either way, I guess. Historically, it was high pressure, liquid. Let's check those answers. Each of these methods separates compounds using charge and polarity. Ion exchange uses charge to attract molecules with opposite charge. Size exclusion uses pores to trap smaller molecules. Affinity uses specific receptors or antibodies. As the name suggests, gas chromatography is simply the same technique of mobile and stationary phase performed with a gaseous eluent instead of liquid. The stationary phase is usually a crushed metal or polymer. Historically, what did I say for gas chromatography? In which way is it distinct? So I guess in high performance liquid chromatography, you also don't have the product at the end. A computer detects it. So it's not distinct in that. It's distinct in that it uses the gas. High performance still uses a liquid. Historically, Hplc was performed at high pressures, whereas column chromatography uses gravity. Now, Hplc is performed with sophisticated and variable solvent and temperature gradients, allowing for much more specific separation of compounds than column chromatography. Higher pressures are no longer required. All right. Practice questions. Number 1, fractional distillation under atmospheric pressure would most likely be used to separate which of the following compounds? Fractional distillation is the one that you use for compounds with similar boiling points, less than 25 degrees Celsius. So 10 to 40 is a 30-degree difference. 77 to 80 is only a 3-degree difference. That's within 25. 84 to 205 is 15, 16 plus 5, 21 apart. That's under 25 degrees. Aniline and water is 184 and 100. So that's more than 25 degree difference. So both of these are within 25 degrees, but let's look at the compounds. B is ethyl acetate and ethanol. Acetate and ethanol. Here we have aniline and benzyl alcohol. Aniline, I'm not sure, but I'm guessing that's organic. Let's look up what aniline, or is it a... Aniline is an organic compound with the formula C6H5NH2. So it's amine, I guess. It is... It doesn't have the oxygen. It's just a... Oh yeah, anything that has a nitrogen atom with a lone pair. And so... Aniline again. NH2, it's got the lone pair. So, it sounds... So we have an amine and alcohol. And here we have acetate and ethanol. And alcohol and acetate is an ester of acetic acid. It seems to me that since this can be done with different functional groups, that Since these have different functional groups, I imagine that it would be easier to separate them with other methods. I think acetate and ethanol would be hard to separate without, right? They have like similar functional groups. Do they have similar functional groups? Acetate is acetic acid that's been deprotonated. So if it's been deprotonated, then it doesn't make hydrogen bonds, while alcohol does. On the other hand, alcohol, in this benzyl alcohol, makes hydrogen bonds in aniline. Does aniline make? It doesn't, right? Do amines make hydrogen bonds? Amines can form hydrogen bonds with water and alcohol. So maybe C, even though their boiling points are further apart than for B, they're still within 25 degrees Celsius. And, but the other factor is being above 150. And in this case, they are above 150. In this case, they are not. So you might have to use vacuum distillation for this. So let's go with B, after all. Two, which of the following compounds would be most effective in extracting benzoic acid from a diethyl ether solution? Benzoic acid from diethyl ether. Tetrahydrofuran, aqueous hydrochloric acid, aqueous sodium hydroxide, or water. So the diethyl ether was the polar nonpolar case, I think. Diethyl ether is organic. Acid is aqueous. Extracting benzoic acid from ether, just water, right? Aqueous hydrochloric acid, aqueous sodium hydroxide. I think just water. Aqueous hydrochloric acid. So if you had water with a really low pH, would that help dissolve more acid? No. Basic water would dissolve more acid. Aqueous sodium hydroxide. Sodium hydroxide would be more basic than water, yeah, so that would do it. Aqueous sodium hydroxide sounds like the best option. Tetrahydrofuran, I imagine, is the organic, right? That'd be, or nonpolar. THF, is that the nonpolar solvent? THF is an organic cyclic ether, water miscible organic liquid with low viscosity. It's water miscible organic, interesting, with low viscosity. Interesting. So, not that one. Aqueous sodium hydroxide sounds perfect. 3. Which of the following would be the best procedure for extracting this acetaldehyde from an aqueous solution? A single extraction with 100 milliliters of ether, 2 successive extractions with 50 milliliter portions of ether, 3 extractions with 33.3 milliliters, or 4 extractions with 25. I guess 4 with 25 is best, right? The more the better. 4 and 5 refer to the table. What would be the effect on the RF values if thin layer chromatography were run with hexane rather than ether as the eluent? Hexane rather than ether. So in this chart, the naphthalene methanol travels the fastest. The alcohol travels the slowest. So the alcohol is most like the ether, while the naphthalene methanol is least. Hexane is more organic. So in this case, we're using ether. Alcohol goes slow, so we're going to say methanol. All right, let's see. Benzyl alcohol, benzyl acetate. We have an alcohol. We have a carboxylic acid. We have phenol, which is an alcohol with a ring structure, stabilized by a ring structure, and then a methanol, naphthalene methanol. So another alcohol, highly substituted alcohol. So more polar, less polar. Ether, like, is most like the least polar. The most polar is not like ether. Hexane is even less polar. So these will go faster. They'll be even less attracted to them. So these values would increase tenfold or double. It's a good question. There's no way of telling. They didn't give us any like actual numbers, did they? Oh yeah, they did give us RF factors. But distance to spot, distance to eluent. get an example of some values. They don't give us real values. I don't know, it just doesn't seem likely to increase tenfold. So I'm just going to say double. But the ambiguity between tenfold and double makes me think that maybe they're both wrong. Maybe it's decrease. So once again, acetic acid versus acetate is already deprotonated, so it doesn't make the hydrogen bonds. Alcohols do make the hydrogen bonds. Yeah, it's got to make them travel faster. Hexane is really going to repel all these molecules. They will travel faster. It's got to be increase. So I'm going to just go with double. We'll see how that turns out. Number 5, if these compounds were separated by column chromatography with ether on silica gel, which would elute first? So ether, silica gel. Oh, retardation factor, not speed. So this is flipped. This is the slowest. This is the fastest. So alcohol, benzyl alcohol and acetate are more repelled by ether, and the more substituted alcohols are more attracted to the ether. So if we had hexane, the retardation factor would go down across the board. Should be decrease. It is decrease. It's D for number 4. Retardation factor means slower, meaning that number should go down with something that repels it more, like hexane. Okay, 5. If these compounds were separated by column chromatography with ether on silica gel, which would elute first? So, the one with the least retardation factor, benzyl alcohol, will elute first. A. 6. 4 compounds, 1, 2, 3, and 4 are separated by chromatographic techniques. Compound 3 is the most polar, 2 the least polar, and 1 and 4 have intermediate polarity. The solvent system is 85 to 15 ethanol to methylene chloride. Which spot on the card below likely belongs to compound 3? So we have chromatography. Compound 3 is the most polar. Compound 2 is the least polar. And 1 and 4 have intermediate. So 1 and 4 and 3 and 2. But which one is 3 and which one is 2? So we're using mostly ethanol, which is polar. So like and like. This should be polar. Compound 3 is the most polar, so this has got to be compound 3. Which spot on the card below likely belongs to compound 3? It's got to be A. We go with A. 7. Suppose an extraction with methylene chloride is performed with the desired compound initially in brine in a separatory funnel. Which layer will be the organic layer? Well, methylene chloride is performed with a desired compound initially in brine. So methylene is going to be your organic. Brine is your aqueous. Methylene chloride's density is higher than the brines, so the organic layer will be the bottom layer. No layers are observed. Methylene chloride and brine are miscible. That's initially what I was thinking. Methylene is organic, but the chloride mixed with the brine. Nah, we'll go with the bottom layer. Let's go with B. 8. Silica gel is often used in thin layer chromatography. What property does silica gel probably possess that makes it useful for this purpose? Silica gel is often used. We know that it has polarity. Aqueous solubility, that's also 2. Specifically sized pores, no. Acidity, I don't think they mentioned that. They mentioned the polarity and that it's hydrophilic. I guess the polarity is really what makes it useful. Let's go with B. 9. A mixture of sand, benzoic acid, naphthalene, and ether is best separated by. You got naphthalene, organic, ether, benzoic acid, aqueous, and sand. I don't know why I put the sand in there. Filtration followed by acidic extraction followed by recrystallization. Filtration followed by basic extraction followed by evaporation. Extraction followed by distillation followed by gas chromatography, or filtration followed by size exclusion column chromatography followed by extraction. Probably not that one. Filtration, first step sounds good, followed by some kind of extraction, followed by either recrystallization or evaporization. It depends on what it is that we want. So filtration to get the sand out. Then you have benzoic acid and naphthalene. So acid extraction, I think you can just do a basic extraction. If you do a basic extraction, you've separated aqueous and organic layers. And then would you evaporate the water to get like benzene or benzene acetate? Or are you evaporating off the ether to get naphthalene? That's probably what you're doing. Acid extraction, getting the benzoic acid and then getting benzene acetate is what you're recrystallizing. I don't know if that doesn't sound as plausible as naphthalene. Crystallizing and organic sounds like what you would do. I'm going to go with B. We'll see in a minute. Number 10, simple distillation could be used to separate which of the following compounds? Simple distillation means under 150 degrees and a difference of more than 25 degrees. So this is low enough because they're both under 150 and the difference is also more than 25. These are under 150 but they're too close together. These are under 150, they're too close together. These are above 150. So it's got to be C. Not even going to read the chemicals. 11. In order to separate a biological effector from solution, which chromatographic technique would be the most effective? A biological effector from solution. Thin layer chromatography, ion exchange chromatography, affinity chromatography, or size exclusion. I think affinity, because we talked about making specific receptors for specific proteins. So let's go with C. 12. Given a solution of insulin with a molecular weight of 5.8 and titin with a molecular weight of 3,816, which chromatographic technique would be the most effective for separating out usable molecules of titin? Thin layer chromatography, ion exchange chromatography, affinity chromatography, or size exclusion chromatography? Let's go with size exclusion since they have such a difference in molecular weight. Affinity chromatography, we could really target insulin, but getting a usable product is supposedly difficult. Yeah, so we'll go with size exclusion. Ion exchange, they didn't talk about the difference in polarity between these molecules. Polarity or rather charge or polarity for thin layer. So yeah, size exclusion it is. Number 13, the gas eluent in gas chromatography and the liquid eluent in paper chromatography are examples of which components of these systems? The eluent is the mobile phase. 13, B. 14, during gravity filtration, a student forgets to heat the solution before running it through the filter. After capturing the filtrate, the student analyzes the sample via infrared spectroscopy and finds one of the desired products in the filtrate. What likely occurred to the student's product? The product degraded because of a prolonged filtration time. The product evaporated with collection of the filtrate. The product precipitated and is present in the residue. The product was dissolved in the solvent. What's gravity filtration? Is that column filtration? Because I didn't think you had to heat stuff up for column filtration or column chromatography. Are they talking about fractional distillation? Because that also kind of uses gravity, right? What are they talking about? Gravity filtration, in which the solvent's own weight pulls it through the filter. Gravity filtration, in which the solvent's own weight pulls it through the filter, is more commonly used when the product of interest is in the filtrate. Hot solvent is generally used to keep the product dissolved in liquid. So if it's not dissolved in liquid, then it's not getting filtered out and it just comes out in the residue. Great. The product was dissolved in the solvent. No, the product was not dissolved in the solvent. The product precipitated and is present in the residue. C. 15. Lactoferrin, a milk protein, is a valuable antimicrobial agent that is extracted from pasteurized defatted milk utilizing a column containing a charged resin. This is an example of which of the following chromatographic techniques? That would be ion exchange chromatography. B. Let's check our answers. 1 is B, 2 is C, 3 is D, 4 is D, 5 is A, not D. Or D, not A, rather. In column chromatography, as in TLC, the less polar compound travels most rapidly. This means that the naphthalene methanol with the highest RF value would travel most rapidly and would be the first to elute from the column. What? 5. Which would elute first? The one with the least retardation factor. They're saying with the one with the highest retardation factor. Okay, I was wrong about retardation factor. It's not how slow it goes, it's how fast it goes. Distance to spot divided by distance to element. So if it's like 9, if it's almost 1, that means it travels fast. If it's 0.01, it means it travels slow. So faster is a higher number. So why did I get number 4 right? I said decrease. This is the fastest. This is the slowest. Hexane is not like. Hexane is different. so is more different, so it'll make them go slower. So 4 is right, and 5, because naphthalene methanol is fastest, it will elute first. All right, 5 is D, 6 is A, 7 is B, 8 is B, 9 is B, 10 is C, 11 is C, 12 is D, 13 is B, 14 is C, and 15 is B. So that is separations and purifications. And that is it for organic chemistry. I think next time we will be getting into biochemistry. Thanks for watching. I'll see you next time.